We continue our study of geometry of sets, picking up from maybe 2 videos ago, where we started discussion of projection of sets and the behavior of Hausdorff dimension under these projections. Just as a heads up, the series on geometric measure theory is going to end soon on this channel. I will explain that the follow-up really is already on YouTube in Azam's channel, where he focuses on rectifiability. So I will try to kind of end in the right place so that you can pick up from there and continue study of rectifiable sets if you're interested by watching his videos. Maybe we'll have 4 or 5 more videos in the geometry of sets realm, and then we move on to the next topic. Anyway, the projection theorems concern the question of how the dimension change of a set when we project it onto affine subspaces of the Euclidean space. The simplest case and the easier to draw is when we have a subset E of the plane, and then we fix an angle and we project the set onto that line. It doesn't matter if the line is through the origin or not, because it's invariant under parallel translation. So you can assume all the lines are through the origin. So theta is, say, from 0 to pi along the semicircle. So when we say almost every theta, we mean with respect to the Lebesgue measure on this semicircle. It's easy to just transfer the Lebesgue one measure onto this bent curve. So that's clear, kind of. The main theorem of Marstrand that we saw was that if you have a Suslin set, which includes the collection of Borel sets, and its Hausdorff dimension is S, then in the 2 regimens we have 2 different behavior. If S is less than 1 or equal to 1, then the dimension of projections is again S for almost every theta. That means we never go strictly less than S in the dimension. And this can only be true if you add almost every theta, because if you have a line perpendicular to the blue line, the projection just becomes 1 point. So this is an almost everywhere claim, which is typical of geometric measure theory results. If S is strictly bigger than 1, so the set is more than 1 dimension, the projection is not only 1-dimensional, you actually see a significant shadow of the set. So the H1 measure of that projection is positive. So the reason for this second video on the topic is to get into the details of the case of S equal to 1, which is the interesting case because it's an integer. So in this case, we will see that there are 2 distinct behavior depending on how nice the set E is. And to motivate that, let's look at some example. If you have a line like the nicest 1-dimensional object that you can imagine, so if this is your set E, what happens is that its projection is good. The projection in theta direction of E has positive measure for all theta except for 1. And that is when you choose the direction perpendicular to Y, to E. So when you project onto that, you just see a single point. Any perturbation of that, any epsilon change from that direction will see a positive measure shadow. And then by analogy, you can imagine that for a, say, C1 smooth curve, this also has to be the case because you can look at one point and then you zoom in. It has a tangent, so the set is basically just similar to a line segment, and same claim actually holds. So there is this lemma 5.4 from Falconer's book. Sorry, this is 6.10 from Falconer's book that says if E subset of R2 is a regular of one set. So I have defined this before in the videos. This is regularity in terms of the density, so that the upper one density of, so I have other densities in mind, so I don't remember the notation. So upper one density of the set E at x is equal to 1 for almost every x in E. So if your set has positive and finite one measure, and also the density has no exceptional points up to a set of measure 0, then we called it a regular one set. So the lemma in Falconer says that if you have a regular one set, then H1 of projection onto theta of E has positive measure for all but one theta. This notion of regular one set probably is not as commonly used in modern geometric measure theory textbooks, because it is actually equivalent to being one rectifiable, if you're familiar with that. If not, it will come up again in follow-up videos. So this is the more familiar version of this to some people will be that if E is one rectifiable, then the projections are positive. Usually you don't have this with but one theta. Definitely it's true for almost every theta, but I also will bet that this is still true if you replace regular one set with one rectifiable. One has to be careful with blindly just generalizing, but usually one is only interested in, I mean, the case of getting it for almost every theta is just as important. Okay, then these are the nice sets, right? So nice one-dimensional sets have this density estimate, and then, I mean, density regularity of regular points everywhere, and then we see that the projection is really nicely behaved there. But then we also saw one-dimensional sets that were very non-curve-like, so non-regular, well, in Falconer's terminology, irregular one sets. An example that we started the series with was that of the counter four corner sets. So you had these four corners and then you kept removing from the middle and so on. This was a multiplication of a 0.5 dimensional counter set here with itself, so it was C cross C. And from, for example, our dimension of product sets results, we know that the dimension of this set is actually 1, so let's call it C just. And actually H1 of C is also equal to 1, but we don't care that it's finite and positive. And at almost every x in the set E. Here E is my counter set. So let's be precise, at H1 almost every, here the density, the upper and lower density, the density does not exist. So the upper and lower densities are not equal, so definitely they're not equal to 1. And that is by definition what we call irregular set. So the projection theorem, the projection claim about irregular sets is that, and this is Theorem 613 from Falconer, that if E is irregular one set in R2, I will repeat it, then H1 of projection onto theta of E has 0. Measure for almost every theta. This is kind of a more surprising fact when you see it for the first time compared to the previous version with curves, because that is what we expected. We have a line or a curve, so its projections are significant. But this is saying that you have a set in R2 which does have positive length. Still, all the shadows miss it. So if you shed a light from any direction, then the shadow here on this line will be negligible. You will not see a positive one-dimensional measure set. And this is again for almost every theta. With the counter set, we actually previously saw at least one exceptional theta. And who remembers that? Try to remember. There was one direction onto which the projection of this set was actually a full segment, and that was y equal 1/2 x. So if you project in this particular theta direction, you actually see a full segment, so definitely positive measure, but that's again only one theta. I think there's another one, but other than that, for almost, so for the rest of theta, it has 0 projection. So that is the dichotomy in dimension 1. So if a set is one-dimensional, by simple exhaustion argument, you can write it up. There's actually a separate video about this, by the way, that it is a union of the irregular part of the set and the regular part of the set. So the study of projection behavior of one-dimensional sets is clearly and cleanly divided into two cases. If your set is regular, then the projections will have positive measure as expected. But if they are irregular, then you never captured the set from its projection. It's kind of it's an object that you can not see through X-rays. If you take X-ray images from a million locations, you still do not see the set. When we define and make precise the definitions of rectifiable and purely unrectifiable sets, we will repeat these theorems in that terminology, which is the terminology, as I said, that has been picked up by modern textbooks, maybe more than the regular and irregular set. Another question of still current research is, what more can we say about the exceptional set of directions in either case? About that, hopefully I will also look at some introduction of papers where they start with that. But hopefully this was useful, and see you in future videos.